Okay, congratulations. You are on the last paper that I gave you. We are doing probability. I'm in 7th period right now. Give a shout out.
I'm back.
All right, we just got our EOC scores back and we're pretty darn excited. So we're going to keep working hard and get this done. So some things to know for probability. First of all, probability is whatever you want over everything possible. That's the generic probability formula. What you want over everything. Now, it's a little bit different if you see the word given, because that's going to change. It won't be everything, but in essence, it's everything possible. That says an E, even though it looks a little curvy. Okay, so sample spaces are all the possible answers that you could get. So if you're looking at a coin, your sample space would be heads and tails because you could only get heads or tails. It's not like you can get the number 4 on a coin. The sample point is each outcome. An event is a group of possible outcomes. Here you will have to know this. This is one of our fundamental geometry things. U stands for union. If something is the union, it is either A or B or both. So you need all of it. Think of it, 2 people getting married. One person's, all their stuff goes to the house. All the other person's stuff goes in the house. Everything comes together. Union. That's different than the intersection. The intersection, think of it as 2 streets meeting up at a stoplight. Our intersection is just this little part right here where they meet. The intersection is the overlap. It's what they have in common. So our same couple, their intersection when they get together and have a little baby, that's the intersection. It's what they have in common. That's the overlap. Okay, so in order for it to be like that, it has to be both of these. Now, you might see this last symbol. That last symbol, sometimes kids call it like A prime, A with a little line. That line means not. So it wants everything that's not in A. Next, let's look at things like mutually exclusive. You had one of these questions on your probability test. Mutually exclusive versus independent events. Now, mathematically speaking, if something is mutually exclusive, it's the probability of A or B happening, but not necessarily both. So for example, it's the probability of me getting a red Skittle and a green Skittle, but it's impossible to get a red-green Skittle. So that would be mutually exclusive. I could get a red or I could eat a green, but there's no such thing as a red-green Skittle. Maybe there is. I don't know about a red-green Skittle. Independent events, you have this formula, and this formula is what's on your formula sheet. So if you are given probabilities or numbers or decimals and it says independent, you have to use your formula sheet to get that independent thing. Now, here's where it gets a little tricky. Even though mathematically speaking, independent and mutually exclusive are different, which is true. Mathematically speaking, looking at the formulas, those are 2 different formulas. But sometimes some mathematicians, they will interchange those terms. They'll say independent when they talk about stories when they really mean mutually exclusive, or they'll say mutually exclusive when they really mean independent when they talk about stories. So let's take a look at some examples. Down here, if we have something that's independent, mutually exclusive, it will either include the words with replacement. So it's like I looked at my red M&M and then I put my red M&M back. I didn't eat it, I put it back. With replacement, it would be independent because I didn't eat it. Buying toilet paper at the store and buying a steak. Hopefully there's no correlation between buying toilet paper and buying a steak. Now there might be if you went and bought like baked beans, but not really for a steak. Going skiing and visiting Florida. Now if it was water skiing, that might be dependent, but you wouldn't necessarily ski down mountains in Florida. That'd be independent, mutually exclusive. Reading a book and doing sit-ups. Now you might be able to listen to a book doing sit-ups, but it might be a little bit challenging reading a book and doing sit-ups at the same time. 2 completely mutually exclusive, independent, not related to each other events. Flipping a coin and drawing a card. Just because you get heads on a coin doesn't mean that you'll get a certain card from the deck. They're not related. Now that's different than dependence. When you see something with a dependent, you will either see something that says without replacement. Without replacement means you ate that M&M or you ate that Skittle. It's not coming back up. It's in your body. It changed the number of Skittles or M&Ms that you had. Or, as before I said, like mutually exclusive would be buying toilet paper and a steak, but it might make sense if you go to the grocery store and you buy peanut butter and jelly because you're probably making a peanut butter and jelly sandwich. If it's raining outside and bring in your umbrella, that makes sense. It's raining outside, you bring your umbrella. If you eat healthy, you most likely will be losing weight. So those would be dependent on each other. You have to have one with the other, or you could see one with the other. So for example, I see trees with leaves on them. So that would be dependent because it exists in the universe. So there's trees with leaves on them. Now, I've never seen a tree with marshmallows. So that would be independent or mutually exclusive because I've never seen that before. So dependent is you can see it together. Independent is it doesn't necessarily make sense. Let's do some math. Conditional probability. Anytime you see conditional probability, and you likely will, why do I know that? Because it's on the formula sheet, so I expect that they're going to make you know how to use it. You will always see this line going up and down, or you'll see the word given. If you see someone say given something in probability, or you see that up and down line, you're going to know that you're going to use the formula that's on the formula sheet. Here's the trick. Whatever is given will always be the bottom number, even if the formula sheet says something different. So the formula sheet says the probability of A given B is the probability of A and B divided by the probability of B. But what if they ask you what's the probability of B given A? Here. That formula is not on the formula sheet. Dude, all you're doing is the same exact thing, the probability of A and B, but what's on the denominator? A in this case. Whatever comes after the line is always on the bottom. So here's an example. Probability of A, so here it is, A given B happening. So first we find what's the probability of A and B happening together? 2. There's 2 things that A and B have in common right here. Pretty. Then what's the probability of B happening? Well, how we got that is B is this whole circle. So it's the 2 here plus this 3 here. So that's how we got the 2/5. Other things you will need to know. You will most likely need to know about a deck of cards. I tried to turn this into a song, and I did a horrible job trying to turn this into a song, or a chant. But here's what you need to know. There are 52 cards in a deck, 26 red and 26 black. Okay? Think of it like there's 52 weeks in a year. So if there's 52 weeks in a year, 52 cards in a deck. Now there's 2 types of colors. There's red and black. So even if you don't remember 26, if you remember 52 cards in a deck, you can just do 52 divided by 2, and that's going to tell you how many red cards and how many black cards there are. 26 red, 26 black. Within each color scheme, within the reds, there's 2 what are called suits. So in this red one, we've got hearts and diamonds. And in the black one, we've got spades and clubs. So you got diamonds, hearts, spades, and clubs. So now we know there's 52 cards in a deck, 26 red and 26 black, 4 suits in a deck, diamonds, hearts, clubs, and spades. Now we're looking at how many cards. Well, each suit has a total of 10 cards that go ace, 2, 3, 4, 5. So we don't write the number 1. We call that 1 an ace. And then you have these 3 face cards. Now, technically speaking, yes, there's often 2 jokers in a deck. These aren't the types of math that we're talking about. We typically will see jokers when they talk about it. Always think 52, 26, 26, and then it'll be 13, 13, 13, 13. Moving on. Okay, so we're going to go back to this idea of independence mutually exclusive, and I'm going to call on my period 7 kids to help us out. So toss in a coin. Jasmine's so thrilled. And drawing a card. Is that independent or dependent? Independent. Yep, you should write it on your papers. Yeah, you can just put I. Okay? Drawing a ball, now they call it from an urn. I don't know why they would say an urn, but drawing a ball from a container and not replacing it and then drawing a second ball. Dependent. Because it says not replacing, that's just like eating that M&M or that Skittle. Now, this one we've talked about before. Getting a raise in salary and purchasing a new car. Dependent. Now, technically speaking, just because you get a new salary doesn't mean you always will purchase a car. But for the most part, this is what they want you to think is dependent. You could also argue independent, but driving on ice and having an accident. Dependent. Having a large shoe size and having a high IQ. Independent. A father being left-handed and a daughter being left-handed. It is dependent. That's gene related. Smoking excessively and having lung cancer. It's dependent, right?
Yeah.
Okay. And then this one, eating an excessive amount of ice cream and smoking an excessive amount of cigarettes. I would say independent, but who knows? Who knows? All right, here's our next question you're writing down, folks. Last year, there were 36 pupils in a class. Of these, 20 studied French, 9 studied German, and 3 studied both. So right away for me, I'm just going to draw a Venn diagram. So you two will also draw a Venn diagram. We're going to have 2 circles. Here's our first circle. Here's our second circle. Switch colors. All right, for our sake, we're going to call this side German. Actually, I should have made that French, but I don't think I can erase. Can I erase? Oh, I can. Let's erase. So I will have that first side be French, and then we'll have our next side be German. So I'll put an F here for French. This side is German. So now it says 20 students did French. Now this is where it gets confusing. That whole circle is 20, not just that little piece. So we know that this whole circle has to be 20. This whole circle has to equal 9, and the inside has to equal 3. So that's immediately what we're going to do. We're going to put a 3 in the middle, and then we'll work backwards. So that overlap is 3, because 3 kids did French, and 3 kids did French and German. So now if we know that French is 20 kids, class, and 3 are in the middle, yeah, we know that 17 only took French. If 9 studied German and 3 took French also, how many only took German? 6. Okay. Now, it tells us that this whole box has to have 36 kids. Here's our whole box, 36. So with this whole box having 36, anyone know what we got to do? Excellent. We add these together, which is 26. And then we subtract from 36. So we've got 26, 17 and 3 is 20, plus 6 is 26. There's 36 all together. So that means there's 10 people who did not take it. Now, we're not done yet. We wouldn't write 10 people because the question says, what is the probability that the person does not take it? So now we have to put 10 over 36 because there's 10 kids who didn't take it divided by 36. And then you would reduce your fraction. Okay, I was going to say, it's definitely not 2.7, but 0.27. Thank you, Corey. And that's our probability. Yeah, 0.27, 27%. Technically, if we turned it into percent, we would do, actually, it's actually not that. It's 28 because the decimal is 0.277. So if we wanted to do proper rounding, it would actually be 0.28. Okay, next, done. From a deck of cards, here's a deck of cards question. 2 cards are being chosen without replacement. Okay, this was nice. They told us that there were 52 cards to begin with. What is the probability that the first one will be black and the second one will be red? So we know 2 things are going to happen. Now, I've told you in the past that when you have multiple probabilities, you multiply. The only time that you don't is if it says or. Multiple, prob, multiply. My cursive is getting awful. So, first of all, we know that there's 52 cards in a deck, so that's going to be our first number. It doesn't say the word given, so we know it's going to be 52. Now it says first one's being black. So how many black cards are there? Anyone? 26. Now we're going to assume that we got the black one first. So we know we're going to multiply. Now we need to know what's the probability the second one is red. Well, if it says without replacement, how many cards are left if I'm holding a card in my hand? 51. Now, if I pulled a black card, how many red cards are left? 26. All right, so we wouldn't put down 25. Sometimes they trick you. Sometimes they'll say if the first one's black, the second one's black, you'll have to subtract from the top and bottom. It would be 25 over 51. But because it's only the first red would be drawn, it's 26. you can do 26 times 26 on the calculator, which is 676, divided by 52 times 51, which is 2,652. 676, 2652, which gives us 0.254. So we can just put 0.25. So 1 in 4 chance that your first one will be black and your next one would be red. Oh, did I do the same question twice? What's your fourth question say? Is it the same one? Woohoo! Cross that out. That was my mistake. Next, I think this is our last one for probability. High school has 100 students. 80 of them play soccer, 70 play softball, and 10 play neither of the two. How many students play both soccer and softball? This one's really tricky. So I am going to draw a picture. And we know that there's two sports. So we have a circle here and we have a circle here. We know that there's 10 people who are outside the circle. So really the 80, 70, 10 have to somewhere get involved, or the 80, 70 is in the circles, the 10's on the outside. So what we're going to look at is we're looking at that represents 100 students. I'm going to do 100 minus 10. And when I subtract the 90, I have 90 to play with. Now, we don't know what the overlap is. So I'm going to call that overlap X. Now, we did on the other problem that we just subtracted the overlap. That's all you're going to do here. Here we're going to have 80 minus X. Because we don't know what X is, so that's just going to be 80 minus X. This side will be 70 minus X. Because we don't know how much that overlap is. All that overlap is to us is X. Now, we know that when we add these three parts up, we should get 90. So I'm going to write 80 minus X. I think this is more challenging than what you'd see on the final, but let's just do it to make sure. 80 minus X plus 70 minus X. And all of that equals 90. And it doesn't equal 100 because we know 10 kids didn't play sports, so we don't include those. So these would cancel. Shift colors. So X minus X, negative X plus X is 0. 80 plus 70 is 150. Minus X equals 90. I'm going to subtract 150 from both sides. Which gives me negative X equals negative 60. So we would divide both sides by negative 1 and get X equals 60. So now we can go in here. Oh, that's just what we needed. 60 kids do both. 60. So if a student is chosen randomly, so far so good, do you need a second? If a student is chosen randomly, what is the probability this student plays only soccer or only softball? So we know there's 60 here. 80 minus 60 means there's 20 kids that only play soccer. And 70 minus 60 means there's 10 kids that only play softball. So what we do is we find what's the probability a person plays soccer? Only soccer, 20 out of 100 kids. Because we're still counting the 10 kids who don't play. So then it says or. So if it says, see how it says or? Formula sheet. The addition rule right here tells us that we would do the probability of A plus the probability of B and subtract A and B. Now in this case, because we're only doing the only parts, we don't have to subtract anything. All we're doing is adding. So you've got basically 20 plus 10 over 100. Which gives us 30 over 100. Please don't put 30 over 200. Remember, we don't add the denominators down. Denominators stay the same. So 0.3. Given, woohoo! Okay, so I am back. Oh, because I messed this up, but it didn't delete it. So let me just get my eraser tool so you can see. And let's do C again. So what I missed is it is given, and that is the formula. But for some reason, I put the probabilities in the fraction instead of the numbers. So let's take a look at that one more time. So given it's softball, I'm going to have my total number of softball people on the bottom. And we know that altogether, 70 people play softball. So I'm going to put 70 in my denominator. Then it says, what's the probability they play both They play both. We discovered in this first part that 60 students play both. So all our answer is literally that easy, and I made it way harder. It's just 60 over 70. And then when we get our decimal, I think it's 83%. I don't remember. Let's take a look. Nope, 85.7%. 0.85. So that'll give us 86% when we round it. So next, determine whether these events are independent, soccer, or softball. So for independent, and it has to do with probabilities, we're going to have a formula sheet. Really? Because on our formula sheet, it tells us that independent says if the probability of A and B happening, that equals the probability of A times B. So for soccer, the probability, I don't even know if I want you to do this. Guys, we're not going to do this question. Exit out. Done. This is not a good example. You're done. Woo!